This is a mock-up of an electrically actuated variable pitch propeller. This is not the demo, just inspiration. Commercially available systems, like the one from Airmaster, use the same principle to set propeller blade pitch to different angles for takeoff, climb, and cruise. The problem here is getting electricity into the propeller hub while it's spinning. Slip rings with graphite brushes are the common solution, but they come with reliability and maintenance penalties. This mock-up has been built around a PCB with 3 layers of coils embedded in it to see if we can use the relative motion between the engine and propeller along with the magnetic field to generate power for the system in situ. This DC motor will represent the plane's engine, and the permanent magnet rotor would be fixed to the front of the engine. We have reversed the rotating and fixed relationship from the real application for demonstration purposes. As we spin up the rotor, you may notice that the system is imbalanced, causing heavy vibrations. This is pretty terrifying, but I have this safety board to hide behind, so it's okay. The system needs a very small air gap to work. So as we bring the rotor and stator together, we start to see nothing. So what's going on? I've taken a spare PCB with no components to check the phase-to-phase voltage. As the motor starts, an AC waveform appears, and the faster we go, the higher the voltage. In this test, we reach about 8 volts peak to peak, and in others, I have seen as high as 10.5. We are clearly generating some power here, but the microcontroller was still not turning on. In tests, the mock-up system runs on 5 volts and about 100 milliamps. The generator voltage has to be designed into the system, while drawing additional current just increases the torque demand on our drive motor. Since this motor is way oversized, we should have plenty of headroom there. Taking another spare board, this time with a 3-phase rectifier in place, the problem becomes apparent. The noisy DC voltage measured here is only about 3 volts. This is because the DC voltage is related to the root mean square of the AC waveform. If we have 8 volts AC peak to peak, with a corresponding amplitude of 4 volts, we expect an RMS voltage of 3 volts, which is what we're seeing. The propeller mock-up we designed needs 5 volts to operate, so what can we do? Adding more turns to the coils would be the best way to up the generated voltage, but ordering more PCBs is a no-go. Faster rotation would also do the trick, but with the imbalance issues, that is super risky. Instead, we focused on adding more magnetic poles to the rotor, which also effectively increases the speed of the system at the same RPM. Here you can see a portion of the work done toward this end, including the original 6-pole disc and a plywood one that exploded in my hand. While it's disappointing to stop here, I believe we have at least demonstrated the concept. The system clearly needs more engineering, but we did generate power in situ using an axial flux generator topology.